There we are. Thank you very much. So, welcome back to the final of our series of Welsh lectures this year. I'm Ephraim Steinberg from the Department of Physics. And since as was already the case yesterday, our speaker needs very little introduction in terms of the objective facts of his career and what he's famous for. I want to follow He Young's lead and just take the opportunity to say something a little more personal. Alain told me that I have the right to say anything I like, but he has the right to contradict me, which of course is in keeping with what we should all expect from the great scientist. You heard yesterday from Steve Kivelson that for many people, there's nothing more fun than talking and thinking about quantum mechanics. And those of you who know me know that I'm one of the people in that camp. And in fact, if you've taken my class, you've probably heard me say that Bell's theorem is one of the two greatest intellectual achievements of the 20th century, one of the things that shook our understanding of the world and nature. And I want to go back in time to when I first learned about it, because it was when I was a teenager reading a science fiction book that it actually mentioned these Bell's theorem that I just completely couldn't get my head around. And in the glossary said that someone named Aspect had done experiments to prove these deep facts about reality. And at the time, I was young and my sense of time was maybe a little different than it is now. And the book threw out names like Schrödinger, Heisenberg, Bohr, Bell, Aspect. Obviously, it never occurred to me that I would ever have the privilege to meet Alain in person, let alone to be introducing him to you. And I think that's really one of the great things about being a physicist. We get a chance to meet our heroes. And Alain was the first of my real heroes that I ever had the opportunity to meet. Although the first time I nearly met him, it was striking to me. I was working for a year at the École Normale Supérieure before graduate school. And somehow Alain's experiments came up in discussion and someone said, well, you should just ask him. And I said, what do you mean ask him? And they said, well, he's just working down the hall. And I had no idea, as I said, it was Schrödinger, Bohr, Aspect in my mind. And I said, well, who is he? And they described him. And I said, you mean the guy who asks a question after every single seminar? That's Aspect. And that's part of what I want you to remember. Not only did he have the courage to explore something that was so far from the mainstream, but now recognized as being so important, but he's someone who, no matter what the talk is about, no matter who he's talking with, wants to learn and always has a deep new question. And if we can all try a little bit to emulate Alain, both in his courage, in his openness, and as was mentioned yesterday, in what an amazing mentor he is and how kind and open he is to younger people, our department and the world will be a better place. So with that, I want to introduce my hero, Alain Aspect.
Merci, Ephraim. Ephraim speaks a perfect French, so because the seminar is for him, I will do it in French. But you will have English subtitles, so you can follow. Okay, today is supposed to be a colloquium, so I'm going to be a little more technical than yesterday, although it will cover a part of what I said yesterday, but it's so exciting. Bell's theorem is so exciting that it does not hurt to hear twice about it, because at the end there is an exam, okay? By the way, this I should have presented yesterday. This is a small book. I tell a story. I tell the story of Einstein and the quantum revolutions. And this book sells quite well in France because there is no equation. It's really a book which can be read by anybody who is interested, but who has no education in science, doesn't know about equation. You can offer it to your grandmother or your aunt, okay? And of course, if your grandmother or aunt doesn't speak French, for the moment, it's not very good, but it is, well, it is in print by Chicago University Press, and so it should be released in a few months, okay? And it turns out that it is a book that sells very well for the reason I told you. It was advertised not by me. It was advertised by people on radio programs saying, by the way, I read a book on quantum physics. And when somebody offers me a book on quantum physics, I say, oh, no, that's not possible. It was fascinating. And so the next month, I sold 2,000 or 3,000 of them, you know, and so honestly, it's not for the royalty I get for it, because the price, at least in France, is €8, which is basically $8, okay, or something like that. So you can guess that I don't get much money out of it, but it's fun to have. Okay, let us start. How did new quantum technology emerge? So you remember there was a debate between Bohr and Einstein in 1935. Schrödinger immediately realized how surprising entanglement is. So let's say that these three people in 1935 put the finger on how entanglement is amazing. Then another 30 years, well, 29, John Bell realized that not only it's amazing, but it is different. Different of what? Different of what people thought to be amazing in quantum physics. In other words, as I told you yesterday, basically they only thought about wave-particle duality and these kind of things. And entanglement is about two particles, and it's really different. And now comes Feynman. Feynman, in 1958, something like that, in his lectures on physics, speaks about Einstein-Podolsky-Rosen. And he says, nothing special. Einstein-Podolsky-Rosen, same as my previous chapter on single particles in young slits or something like that. But 20 years later, in this paper, in 82, Feynman say, oops, maybe I missed something. And then in this paper, he develops Bell's inequality without citing Bell. Probably he rederives it for himself. And he cites the experiment of Clauser and Friedman. No, he doesn't cite them. He says there is an experiment where you can measure it, etc. But Feynman, being Feynman, as soon as he recognizes that there is something exciting, he says, what can we do with it? And he lays the ground for quantum computing. And the first idea of quantum computing are in that paper of Feynman. Okay. So entanglement is at the root of many quantum technologies. But these quantum technologies, as I told you yesterday, and I will repeat it today, especially because obviously there are people who were not here yesterday, these quantum technology are also based on the fact that in the last decades, physicists and engineers have learned how to observe, control, manipulate single quantum object, which is something which had never been done before 1970s. So for you, 1970s is prehistory. But for me, I had already graduated. I was already an advanced student in 1970. So I could acknowledge this first appearance of manipulation of individual object. Okay. And I will finish by asking the question, do we live a new quantum revolution, a second quantum revolution? So let us start with the Einstein-Podolsky-Rosen Bohm Gedanken experiment showing strong correlation at a distance. Okay. So the reason why Einstein thought that quantum mechanics was not complete is that he was worried by the fact that the result of the calculation of quantum mechanics give probabilistic result. Einstein had no problem with probability. His paper of 1905 about Brownian motion is a masterpiece on use of probability. So he has no problem with probability, but he thought that an ultimate theory should not use probability. Use of probability is convenient for complicated problems. For instance, if you want to describe the motion of the molecules in this room, you are not going to succeed. You have 10 to the 24th, you are not going to succeed. So you are going to make statistics, say what is a fraction of the molecule having a velocity between this and that. But you have no doubt that below this statistical description, there is an ultimate theory where in principle you could describe the molecule bouncing on each other, etc., etc. Apparently, that was the idea of Einstein. And for this reason, he said, quantum mechanics is okay, but it must be completed by an underlying description more precise. And he tried first with single particle. He tried first to show the possibility to know both the position and the velocity of a particle better than allowed by the statistical description, that is to say, by the Heisenberg uncertainty relation, okay? He did his best. He said, look, if I do that, I can measure both the velocity and the position better than allowed by Heisenberg. And there was a famous debate with Niels Bohr at the Solvay conference of 1927. And each time Bohr came and said, look, you forgot something. You forgot that the moving slit is also a quantum object, etc., etc. And Bohr replied impeccably to Einstein on all these arguments, which were all bearing on single particles. So in 1935, he came with something new, two entangled particles. And with these two entangled particles, he came with a totally different line of reasoning from which he concluded that quantum mechanics is not complete. And this is what I am going to show you now. So normally I have a small pointer and something like that, but because I brought my luggage in the plane, they would have taken my laser out of it. So I did not bring my laser. I am sorry. So the idea is the following. Here, I am going to do a measurement of polarization, and most of you, but anyway, I'm not sure that not all of you may know what is a polarization measurement. This is a system which is allowed to tell me when I have a wave arriving here, what is the direction of oscillation of the electric field. When you have a wave propagating, a light wave, electromagnetic wave, the electric field is vibrating perpendicular, and you see that means that it is in a plane, so the polarization has a certain orientation. This apparatus allows you to tell what is the orientation of the electric field. It has a direction A, and if the light is polarized along A, the beam will go out in channel +1. If light is polarized perpendicular to A, it will go in -1. And if the light beam is polarized at an angle, a fraction of the beam will go up and a fraction of the beam will go out. For those who are the course in optics, it's called the Malus law. Now, if you have a single photon, the photon will not be split in two. There will not be a part of the photon up or part of a photon down. So if the single photon are polarized along A, they will all finish in +1. If they are polarized perpendicular to A, they will all finish in -1. And if they are polarized at an angle, a fraction of them will arrive in +1, a fraction in -1. And now we have the probabilistic prediction of quantum mechanics. You tell what is the polarization, you make the calculation, tell you 30% of the case it goes here, etc., etc. So we are going to do the experiment, measure the probability to get +1 or -1 here, probability to get +1 or -1 there, you know, with orientation A for the first polarized, B for the other one. And we are going also to do something which turns out to be very interesting. We are looking at the joint probability. I have a pair, okay, one photon to the left, one photon to the right. So I will have a detection here, detection there. What is the probability to get +1, +1, or to get +1, -1? So 4 possible probabilities. So I repeat the experiment a large number of times, I get these probabilities. Up to now, no Einstein, Podolsky, Rosen, no quantum mechanics. Now comes Einstein, Podolsky, Rosen. They discovered that the formalism of quantum mechanics allows you to consider states which are entangled for two particles. I explained for those of you who are not comfortable, and the other one, you can relax, okay? You know what I am going to say, you relax. What does this mean? If I had only XX, it would describe a pair of photons which are polarized along the vertical axis, okay? If I had YY only, it would describe a pair of photons along the horizontal axis out of the screen, okay? And the formalism of quantum mechanics tells you that if this is allowed and if that is allowed, The sum of the two is also allowed. So now I have a pair of photons which are both this and that. What does it mean? It does not mean, for instance, polarized at 44 degree, because if it was the case, you could rewrite that as a product of this by that. And if you know a little bit of mathematics, you will easily discover that there is no way to write that as a product of something for the first photon by something by the other one. There is no way to tell the first photon has such possibility and the second photon has such property. This is a big discovery of Einstein, Podolsky, and Rosen, this entangled state. Now, let us do the calculation. If you have an elementary course of quantum physics, you are able to do this calculation, and you can calculate P plus, P minus for that state, and you find 1/2, which means that when the photon arrives here, there is the same probability to go up and to go down. Same on the second side. Now, what is interesting is to calculate the joint probability. And when you calculate the joint probability, you find 1/2 of the square of the cosine of the angle for plus plus or minus minus. And for the cross, you have just the sine square. And you can check in passing that the sum of the 4 probabilities is 1 as it should. And now, this shows something very interesting when the two polarizers have the same orientation, that is to say the angle AB equals 0. Because if the angle AB equals 0, P plus plus equal P minus minus equal 1/2, and the other ones are 0. And I claim that this is a total correlation. And at this point, people say, oh, this guy doesn't know what he's saying. 1/2 is not total. Yes, it is total, and I show you why. The probability to have +1 here is 1/2. And the joint probability is also 1/2. It means that the conditional probability to get +1 here, if I get +1 here, this conditional probability is 100%. Same, if I get -1 here, I am sure to get -1. And if you are not yet convinced, look, P plus minus is 0. So if I get +1, I am really sure to get +1 here. This total correlation. Now, sorry for those who were here yesterday, but, no, I have to finish that. Technically, when you have 2 random variables, you have 1 random variable here and you have 1 random variable there. This random variable, let's say it has value +1 or -1. The other one +1 or -1. Now, the correlation between 2 random variables is defined in your mathematics course, course about probability, as the average of the product minus the product of the average normalized. And when you do that, believe me, or you can do it yourself, it will take 2 minutes if you have a piece of paper. When you do that, you find that it is P plus 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 P minus 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 the cross value. And if you know enough of trigonometry, you find that it is what you have. And by the way, when the angle is 0, the correlation is 1. You know, I knew what I was saying. Total correlation, 1. Okay. Now, how to understand this correlation? Because you have to admit that they are strange, okay? You have a guy there tossing a coin. He finds head of tails. You have another one here tossing a coin, head of tails. Looks random. But when you compare what they find, if he gets head, head, tail, tail, you say, well, this is bizarre. I want to understand, okay? So how to understand? The first good idea when you are a physicist and when you have equations to give you a result is to look into the equation to try to build an image. Well, at least it's my way of doing physics. I love images, okay? So I have equation. I've done the calculation, giving 1/2 of cosine square, etc. Can I make an image out of that? And the answer is no. And the reason why it is no is that these states that I've written, xx plus yy, operates in an abstract space called the Hilbert space, which is a tensor product of the space describing the first particle by the space describing the other one. If there was a single particle, I could make an image. But with two particles, I cannot make an image from that because, once again, the state is not factorable. So it's impossible to extract an image in ordinary space where the two photons are separated. But as Asher Perez, the author of that book, which is an absolutely orthodox and standard book on quantum mechanics, a little complicated, but absolutely standard. He's a believer in Niels Bohr, Copenhagen School, etc. Anyway, and in spite of the fact that he is a theorist, he writes quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. And so I want to make an image in the ordinary space. And in fact, there is a way. There is a way, provided that I do the calculation in a slightly more elaborated way, which is not as efficient as this one, but at the end, I will have the same result to the price of a detour. So let us do it. I'm going to consider that the measurement happens first here. Maybe this polarizer is a little close to the source. Think whatever you want. So the photon arrives here, and I know I can have +1 or -1. And then what do? I go to my Bible. My personal quantum Bible is a book by Claude Cohen-Tanuji, Dew and Lalauet, but you may choose your Bible, provided that it is a normal Bible, okay? And the Bible tells you, just after a measurement, you have a new quantum state. And the new quantum state is obtained by projecting the initial state onto the eigenspace associated with the result. And the projector for this result is xx plus xy. So if I use a projector xx plus xy and I apply to that, there is only one term which is concerned, that this one, and after this projection, I get xx. Now, if I get -1, -1 is associated with the result y. The projector is yx plus yy, and the result of the projection is yy. Okay, so what do I have? I have, initially, I cannot speak of the polarization of each photon. But as soon as I have the result x here, immediately the other photon takes the polarization x. And if I get y, the other photon takes the polarization y. And with this, I immediately understand the full correlation, because I find +1, I have x, it's +1. I have -1, it's y, I get -1. And I can repeat the reasoning with any angle and find the 1/2 of cosine square, etc., etc. So you see, I have a good image, but the measurement on the first photon seems to influence instantaneously at a distance the state of the other photon. Einstein could not accept that. And this is why he concluded that that formalism of quantum mechanics is not complete. He accepted the result of the measurement, but he said, look, it's crazy. If I follow things like that, it means that result of the measurement here influences instantaneously the other side. Is not possible. We have to complete quantum mechanics. What does he mean by completing? Well, it means that when we have two objects which have interacted and which separate, okay, if there is a correlation between this one and the other one, there is an obvious explanation. From the beginning, they are the joint property. And this joint property allows us to understand the correlation. So this was the conclusion of Einstein, that quantum mechanics has to be completed. So both photons bear from their very emission an identical property that we call lambda, that determines the result of the measurement here and there. And of course, because I have randomness, the lambda is not the same for all pairs. For instance, for some pairs, it's from the beginning, you know that the polarization will give +1 result. For other one, you know from the beginning that it will give minus, etc. And you make a theory out of that. I will show you an example. Once again, as yesterday, I emphasize that this image is not only simple and convincing, but it is a perfectly rational image. When biologists or medical doctors conclude that a disease is of genetic origin, it's because they have observed that twin brothers or twin sisters, genuine, okay, twin brother or twin sisters, if they have the same disease, it means that this disease is produced by the same chromosome, okay? So it's absolutely scientific. Anyway, Bohr disagreed. Why? Because Bohr had a deep intuition that if you complete quantum mechanics, something will turn out to be wrong, okay? But I on purpose say he had a deep intuition because the way he wrote it was absolutely not clear. It was totally different from his reasoning of 1927 when he came with a demonstration. Einstein, you are wrong because this and that and that. Here is just words. You know, Einstein, you are not allowed to speak of a quantity if you cannot measure it, if you have not specified the measuring apparatus. It convinces people who want to be convinced. And I would like to signal that this kind of reasoning is a reasoning that some people were doing at the end of the 19th century, beginning of the 20th century. I was not born, okay, but I have read it in books. There were people saying you are not allowed to speak of atoms because you have never seen atoms. You cannot observe atoms. So you are not allowed to speak of atoms. And the poor Boltzmann committed suicide. It's no fun. I mean, come on. But he was depressed because people were attacking him all the time because he was speaking of atoms, although nobody had seen. So the fact that you cannot see something doesn't mean that it is not a good idea to introduce a quantity. Anyway, Bohr said, no, you cannot. And at this point, Einstein was not convinced. In 27, he was convinced, but here he was not convinced. And they went on speaking until their death, okay, in the 50s. And you see here, they are discussing, okay, and nobody cared, or almost nobody cared. And the best reason, well, there is a reason quantum mechanics is extremely successful, but the most important reason is that it really looked like it's too late, and it's finished. You arrived too late here. You will tell him the beginning. Okay, the main reason is that there was no disagreement on the way to do the calculation. Quantum mechanics works. You do calculation, it allows you to explain the facts. You have seen this morning, the speaker tells you, wow, what I like to do is to explain the facts. He's right. So it was explaining the facts, and it was only a discussion about, should I complete or not? But as I told you, Einstein did not disagree on the results of the calculation. So people did not care. Somebody who cared is John Bell, and so John Bell, 30 years later, say, let us take seriously the idea of Einstein that we should complete quantum mechanics. So this gives you a flavor of the reasoning of Bell. He said, okay, a pair of particles is emitted characterized by a property lambda that will determine the result here. So I have a function, capital A, of lambda and of course of the orientation of the polarizer with value +1 or -1. On the other side, I have a function capital B with value +1 or -1. Now, I must describe how the various lambda are distributed. So I have a density of probability, rho of lambda, which is a normal density of probability, positive, normalized to 1. Once I have that, if you imagine, because you have a lot of imagination, if you imagine a function capital A, capital B reasonable, rho reasonable, as soon as you have that, you can calculate the correlation coefficient, which is, as we said earlier, the average of the product. The rest of the terms do not count. The average of the product, the product of the average is 0 and the normalization factor is 1. So this is what you have. So as soon as you have capital A, capital B, and rho, you calculate the average of the product, and you calculate for your specific model the correlation coefficient. An example, a very nice example. The example you are going to think about in, let's say, 3 minutes if you are smart, 10 minutes if you are a little slow. It took me half an hour, okay? You say, okay, from the beginning, the two photons have a polarization, okay? And now I have to describe what happens at the polarizer. Obviously, if the polarizer is along that polarization, I have +1. If it is at 90 degrees, I have -1. And I put the frontier at 45 degrees between the two, okay? So if it is closer to A, it's +1. If it is closer to the perpendicular, it's -1. On the other hand, I know that the problem has revolution symmetry. So I assume that the density of probability is isotropic, okay? 1/2 pi with this angle. With this very simple model, you calculate, and the result here is a red line. That is to say, the correlation coefficient is +1 for parallel polarizer, -1 for cross polarizer. -1 means that if I get +1 here, I have -1 for this one, but -1 for that is that, okay? And then whatever I have in between. On the other hand, the prediction of quantum mechanics, you remember, is cosine of 2 times the angle. So that's the blue line. And you see, for such a simple model that you found after 3 minutes only, it's an impressive result, okay? And so the question is there a better hidden variable model? You know, theorists have plenty of special function, Hanke function, Bessel function, plenty of things like that. Probably they are going to find one of these sophisticated special function to have the red curve fitting exactly the blue curve. So is there a better hidden variable model agreeing with quantum mechanical prediction at all orientation? And the answer is Bell's theorem, which is quite simple. This is Bell's theorem. Bell's theorem is no. No as an answer to the previous question, okay? Bell's theorem tells you that no local hidden variable theory in the spirit of Einstein's local realism can reproduce quantum mechanical prediction at all the orientation of the polarizer. Yes, you remember my example. For parallel polarizer, it works. For perpendicular, it works. But it does not work in between. So this is Bell thinking in front of my experiment. I am especially proud because this photo that was widely released, I don't know where it comes from. It's not me, okay? But it was widely released. And when I look at that, it's exactly my experiment. I'm so happy. Really, it's CERN that released that photo, not me. How does it work? Bell tells you, if I can calculate the correlation coefficient with capital O, capital B, and rho, whatever R, capital B, well, whatever, provided that give +1 or -1, okay? But whatever the form, special function, etc., there is this quantity S, which is the combination of 4 correlation coefficients associated with 2 orientation on one side, A and A prime, and 2 orientation on the other side, B and B prime. So you do a measurement AB, AB prime, A prime B, A prime B prime. You find 4 numbers, and you combine these numbers with 3 plus and 1 minus. Don't ask me why a minus. Because John Bell was kind of a genius, period. He found that a minus sign was a good idea. Maybe he tried many before finding this one, but at the end he found it. Now look at quantum mechanics. Remember this for the prediction of quantum mechanics for an EPR bomb state for photons. If I take this set of angle, pi over 8, pi over 8, pi over 8, we are going to do the calculation together. 2 times pi over 8 is pi over 4. Cosine of pi over 4 is 1 over root 2. So I have 1 over root 2, 1 over root 2, 1 over root 2. Now A, B prime. Now it's difficult. When I double, the angle is bigger than pi over 2 and the cosine is negative. And I have minus 1 over 2, 1 over root 2. But I have a minus. So it's another plus 1 over root 2. And the result is 4 times divided by root 2, which is 2 root 2. Should have told me. 2 root 2, which obviously is bigger than 2. So let us rewind. If I can describe the correlation by a model with capital A, capital B, and rho, S cannot be bigger than 2. But on the other hand, the prediction of quantum mechanics for orientation at pi/8 and like that. For this specific set of orientation, quantum mechanics prediction is 2√2, which is obviously bigger than that. So I cannot reproduce the quantum mechanical prediction for this set of angles with such a model. So now it's no longer a matter of taste, a matter of interpretation. It's a matter of doing an experiment and checking. Either I have more than 2 and Einstein is wrong, or I have less than 2 and we have found a corner where quantum mechanics is wrong. People say, oh, come on, you are not going to destroy quantum mechanics with such a simple experiment. The question is not to destroy quantum mechanics. All reasonable physicists think that any physical theory, one day or another, will find a small corner where it will have a limit. It might have been a limit here. The idea was not to refuse everything in quantum mechanics. Okay, so it becomes a question of experiment. And now, because you are very quiet and very interesting, I see your eyes, I'm going to show you the demonstration of Bell's inequality. I don't do that often, okay? So you have a privilege. It's high school mathematics. At least when I was at high school, I don't know. Consider 4 numbers, x, x prime, y, and y prime, whose values are either +1 or -1. And now consider this quantity, which after all is not that complicated. I can factor x, I can factor x prime. So I have that. Now look, either y equals y prime. This term is 0, and this term is +2 or -2. Or y equals -y prime. This term is 0, and this term is +2 or -2. So whatever you consider, this term has a value either +2 or -2. Now, when I take the average is obviously between +2 and -2. And when I take the average, I replace x by capital A of A, x prime by capital A of A prime, etc., and I have exactly the quantity of Bell. So this quantity is between +2 and -2, period. That's the demonstration. It's not the initial demonstration of Bell. He's a genius, but he did not find the simple way. The simple way has been found by followers, okay? Not me, by followers, okay? But this is a gorgeous demonstration, okay? Now, in order to demonstrate Bell's inequality, it's clear when you look at the demonstration that you need to assume that what happens here does not depend on the orientation of the other polarizer, etc. And this one does not depend on the other one. And the way in which you prepare the photons does not depend on the orientation of the polarizer, which are going to do the analysis. You need that in order to be able to factorize, as I did in the demonstration. And so, of course, you say, well, obviously, it's a good idea because nobody thinks that the result of the measurement here depends on the orientation of the other apparatus. But look, as Bell said in the conclusion of his paper, we are talking of unknown phenomena. There might be some kind of interaction between the two ends. So there would be a way to make this assumption no longer an assumption, but the consequence of the physical principle. And that way would be to change the orientation of each polarizer while the photons are in flight. Because if you change the orientation of this polarizer while the photon is in flight, then the other one, when the other one is measured, there is no time for any kind of interaction to propagate here and tell the second polarizer what was the orientation of the first one. And even more obviously, if you change the orientation of the polarizer while the photons are flying, when they are emitted, they don't know what will be the orientation here. So the rho of lambda, the lambda that they take, cannot depend on the orientations of the polarizer. Okay, so in an experiment, with variable polarizer, you would have a full conflict between quantum mechanics and all the points of Einstein, all the worldview of Einstein. On the one hand, you would test whether or not you have to complete quantum mechanics, and on the other hand, you also use Einstein's relativity. So, you know, it's really Einstein being tested. Okay. Experiments. 3 generations of experiment. I told you yesterday already. Pioneers, Clauser and Friedman in Berkeley, Pitkin and Holt in Harvard. Clauser found quantum mechanics. Harvard did not find quantum mechanics. It turned out that after other experiments by Clauser and Fry, the score was 3-1 in favor of quantum mechanics. And I embarked into a series of experiments starting in 75. I embarked into this experiment not to settle the debate, because there was a consensus that the experiment in Harvard was not that fantastic, and probably Clauser was right. But the point was that these experiments were definitely different from the scheme I have shown. And so I embarked into this experiment in order to make schemes closer from the ideal scheme on which the theory was discussed, okay? And then there was a 3rd generation of experiment. So I will just flash a few facts about my experiment in Orsay. If you consider 3 levels in an atom, these were 3 particular levels in a calcium atom. This level is not degenerate, this one is degenerate, this one not degenerate. If you can put the atom in this level, there are 2 paths for decaying. One path this side, one path that side. Experts are going to ask me why I don't consider that, because when photons are emitted in opposite direction, it does not count. Okay. In quantum mechanics, when you have 2 paths and you cannot distinguish between the 2 paths, you must add the amplitude. So add the amplitude, but be careful. It's not ordinary interference. It's interference in a 2-particle space. It's a 2-photon amplitude. So I add this 2-photon amplitude for this path and that 2-photon amplitude for that path. This is circular polarization. You can re-express this as a function of linear polarization, and bingo, you get exactly the state that you need. This was understood by Clauser. He used this cascade, but the problem is that he did not know how to excite that level. So what he did was exciting some upper level here, and when he was lucky, it was decaying through this. So he had the pair of photons he needed, but quite often it would decay by other routes arriving here, and he had photon nu2, but not the brother nu1, etc., etc. In addition, the rate of production of pairs was small, and moreover, his source was big. And when you have a big source in optics, people who do optics know that it is a problem. Then you need big lenses, etc., etc. I could excite directly with a recently developed method. It was developed in the early 70s. It's called 2-photon absorption. If you add a first photon and a second photon so that the sum of the energy is exactly resonant on that state, you have a very efficient production. And once again, I speak to the people who know optics. In addition, because it is a nonlinear effect, you concentrate the laser, you have a very small source, a few tenths of micrometer, and when you start with a small source, then it's beautiful because your beams are small and your optics is small, etc., etc. By the way, it was anyway a complicated experiment. You have a vacuum chamber, you have 3 lasers to excite the atoms, and then long pipes here. And what you have at the end of the long pipe is a system for measuring the polarization. Each polarizer is at 6 meters from the source. We first repeated the experiment of Clauser and Friedman with polarizer, which were not ideal, okay? Anyway, we confirmed that result, and we did something else. By pulling the detector at 6 meters from the source, we show that entanglement survives large distance, large compared to what? To the coherence length of the photon. There was a debate of people saying, okay, entanglement, it happens at short distance, but not a long distance, okay? So we went beyond the coherent length of the photon, it was surviving. Then first original experiment. It was possible to obtain, nowadays you can buy it on the shelf. That pay, I had to bribe people yes, it was long ago. I had to bribe people at the Philips laboratory in Eindhoven. They were able to calculate for my wavelength and build that for, okay, 1 dozen of bottle of wine. Okay. No, they were friends. They do it for me for free. But I send them anyway some bottles of wine. So, okay. So for the first time, I had 2-channel polarizer. Before, people had only 1-channel polarizer, passing this polarization and blocking the orthogonal one. And then you have a problem, because if you want to know the minus result, you have to compare with polarizer and without polarizer. And you say the difference is -1, but it demands supplementary assumption, auxiliary calibration. You have to assume that the source has a constant rate while you do the calibration. It's not ideal. While here, look how it is beautiful. You do a run, you select your orientation, you do a run, and you measure the 4 number, plus, 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 minus, minus, plus, minus, minus. You do this ratio, it's self-calibrating. The denominator is the sum of the 4 rates, and in the numerator, you have plus, plus, minus, minus, and the minus of the 1. So in a single run, boom, you have a number. It's fantastic. No auxiliary calibration, nothing. The result is here. Quantity S as a function of the angle starts from 2, goes to almost 2 root 2, not exactly 2 root 2 because the experiment is not ideal, goes here and here. So several interesting things on this curve. First, the green curve was a calculation by quantum mechanics taking into account the inefficiency of the experiment. They are weak, but there are some small inefficiency. And the beauty with quantum mechanics is that you can calculate everything, even messy things, as we have seen this morning with the talk of my colleague, okay? Condensed matter physics is very messy, and anyway, quantum mechanics can sometimes do the calculation. Okay, so here we could do the, I apologize for this. Today it's you, yesterday it was Joseph, okay. So the green curve is a prediction of quantum mechanics, and the red box are the results of measurement plus or minus 2 standard deviation. It's amazing. When I saw that, I say, well, quantum mechanics is a good theory. There is no doubt. We violated Bell's inequality by 40 standard deviation beyond any discussion. Okay. Last experiment. What happens? Doesn't work. Whoop, I have lost. You see something? No, something has happened. And restart the program. I hate that. Where are the technicians? Because it's not my computer. It seems that there is a problem. It's because I said something wrong. I'm punished. Try to do something.
You're just trying to advance?
I don't know. It's not my computer.
I
This
see.
is why I prefer my computer. When something happens, I know what to do.
Yes, it's crashing.
Your computer, you hit it. You hit it.
It's just crashing.
Pardon? Déjà 47?
Do you want to take on?
Et ça compte pas.
Dana, do you need to share still? Okay. Is it this one here?
For the one who did not understand well at the beginning, okay, then we'll have a second.
No, it needs to be shared, but it's your physics department's computer, so I don't know. I don't know, uh, I don't know what presentation it is or anything like that.
It's not part of the Zoom call anymore?
No, it stopped sharing it when this crashed.
This is yesterday, not a good one.
Okay. No good?
No.
This one here? Is that the right one?
I don't know, I have to see.
Okay, let's launch it.
Yes, that's that one.
That's it, okay. You know how far along it was?
I mean, it's okay, just, he can move it, I guess. One second.
Is that sharing on your end?
The conclusion.
Sorry, I'm not sure what slide you were on. Do you know what number?
It seems to be correct.
Do you want,
It's today.
do you want me to? Here,
No, that's okay.
I just need to make sure it's on Zoom real quick. I apologize. Just forget it? Okay, yeah, go for it.
Yeah, yeah. Maybe with quantum teleportation, the person on Zoom could come. Who knows? Who knows? Okay. Now I want my pointer. Pointer. Here it is. Okay. So third experiment that we did in Orsay. You remember the idea changing the orientation of the polarizer while the photons are in flight. So for that, rotating an apparatus 50 kilograms, you're not going to do it in a few nanoseconds, okay? And so what we did is implementing a switch here, which is able either to send light here or to send light there. Here, I have a polarizer in orientation A, here, a polarizer in orientation A prime. And if the switch is fast enough, it's just going at orientation A prime, back at A prime, etc. So this is what we did. We built a switch based on the interaction between an acoustic wave in water and light. And this acousto-optic effect with a standing wave allows you either to deflect light based on Bragg diffraction or to let light go straight. Okay. So the experiment was a little more complicated because we had to reduce the diameter of the beams, etc. So it took a little more time for accumulating data. But anyway, after a couple of hours, we got the result. The result was violation of Bell's inequality by 6 standard deviation, which is really convincing for reasonable physicists. And each measurement was space-like separated of the other one, and it was for the first time, okay? And so we had really achieved the dream of the conclusion of Bell's paper. Bell's paper, in his conclusion, say what would be nice is to change the orientation of the measuring apparatus. It was done. It was 82. By the end of the 80s, people began to develop new sources of pairs of entangled photons based on nonlinear effect. And the interest of nonlinear effect in a crystal is that you produce your pairs of photons in well-defined direction, so you can fit them, introduce them in optical fibers. And I already told you yesterday, Nicolas Gisin uses the commercial optical fibers of the telecom company in Switzerland, and he could demonstrate as early as 98 that entanglement survives at more than 10 kilometers after optical fibers. And Zeilinger in Innsbruck did a similar experiment at only 200 meters, but 200 meters was enough that he had time to choose randomly with a random number generator the orientation of the polarizer and while the photon was in flight. Moreover, there was something nice in this experiment. He was registering the result here with the result of the measurement and the time of the measurement. And it's only when everything was finished that he would compare the data and look at the correlation. Okay, it was very nice. Okay, then there have been a full series of experiments, loopholes, closing loopholes, etc., etc. I have no time. Joseph tells me that I have no more time, so no time to explain that. The only thing that I can say is that when the last set of experiments appeared in 2015, I wrote a news and views, or rather a viewpoint, because it's not Nature. I did not want to do it for Nature. In private, I will tell you why. I was not. I did it for the American Physical Society on their physics, which is a viewpoint. And if you go here, you are going to have all details on loopholes, the way loopholes have been closed, etc. And so Einstein's local realism is untenable. That's the conclusion. We have to renounce the world view of Einstein. The world view of Einstein is local realism. And local realism is, I told you that yesterday already, so I repeat for the people who have not understood yesterday, and maybe there are new people today. The idea of Einstein is that if I have a system here, and when I say here, I think of space-time. I have a system here in space-time, in a volume, in a finite volume of space-time. You have in that volume of space-time all the parameters necessary to calculate energy, position of the velocity, angular momentum, etc., etc. You have all the parameters in it. And this ensemble of parameters, Einstein calls it the physical reality of the system that you have here. Now you have one system here and one system there. And the idea of Einstein is that the physical reality of this is independent of the physical, of the reality, which is here, okay? Of course, they can be correlated by the past. This is hidden variable, but there is no direct connection. And so Einstein told in his reasoning, it was in a famous book in 1955, a kind of testament of Einstein. He was discussing that and he was saying, if I was not right that you should complete quantum mechanics, this is what you would have to accept. You would have either to drop the need of the independence of the physical reality present in different parts of space, or accept that the measurement on one system changes instantaneously the real situation of the second system. Okay. Well, Einstein could not believe that. So he was reasoning and saying, this is so crazy that of course you have to complete quantum mechanics. And nowadays we know that it was not true. So we have to accept one of the two things, which actually are not really independent. It's two points of view on about the same thing anyway. The first way, saying that the two systems are not independent, we call it quantum holism, and it will allow to invent quantum computers. And the second point of view, called quantum non-locality, the fact that you can exchange instantaneously, will allow quantum information, quantum communication, etc. Okay. So a few words to finish, different from yesterday. Yes, you see this note. Yesterday the question was asked, you know what it cannot be used, you know why it cannot be used for signaling faster than light. There is something faster than light, you cannot use it to push on a button and have a bomb exploding here immediately. It will explode after a delay, which is less harmful, of course. Okay. So I want to show that the idea of quantum non-locality gives me a fruitful intuition. I already insisted on that yesterday, and I gave the example of quantum cryptography. So I will not repeat quantum cryptography. I will give you the other example, quantum teleportation. So yesterday in quantum cryptography, what I told you is that because it is at the very last moment that the result is done, there is nothing to spy in between. That was the spirit of the reason why quantum cryptography with the scheme of Arthur Eckert, which is not the same as Bennett, and I have to be careful, okay? Brassard is in Montreal. So if you know Brassard, tell him that I said that there is another method, which is a Brassard and Bennett method, that not this one. Okay. It has been demonstrated from a satellite at more than 1,000 kilometers. And now quantum teleportation. I just show you why thinking of non-locality is important. The idea of quantum teleportation is the following. You have the state of a photon here. You cannot never know completely a state. So don't tell me you measure everything and you create elsewhere. It's impossible. You can only have a partial information on a state. Anyway, we are going to transmit it in its totality. That's the idea of quantum teleportation. Okay. So the photon arrives here. You have not an interaction, but a kind of interference with one photon from a pair of entangled photons here. And you are going to do a measurement, which is called the Bell state measurement. The point is that the fact that you do this measurement makes an instantaneous change in the state of that photon. In other words, just as what I explained, because of non-locality, now this photon assumes a certain state. But it's not the end of the story, because the state that you have here is not exactly the one that you had here. You need, in addition, to look at the result of the measurement here, send the result of the measurement by a classical channel, and have here an electro-optic modulator that will modify that. And then, at the end of the operation, then you have the photon after this operation, which has exactly the same state as the initial state. In between, you have destroyed the first photon, so you have not copied, you have cut and displace, okay? You suppress and you put it there, okay? Now, where is non-locality? Non-locality is in the fact that when you do the operation here, instantaneously, this one is changed. But you have to wait for the arrival of a classical signal. So what you need to have is a quantum memory. So Nicolas Gizen did that experiment by having a long optical fiber for waiting for the arrival of the classical signal here. So you need a quantum memory. And I can tell you, it's by thinking in terms of non-locality that I realized that you need a quantum memory. I was not the first to realize it, but when because I was preparing a problem for my student. When you have a problem for your student, you have to double check things. So I sent a message to the inventors of the method of quantum teleportation, and I say, look, it seems to me that if you don't have a quantum memory, it will not work. And the reply is, yes, you are right. We wrote half a line in our paper for signaling that. In fact, young people who are ambitious try to develop quantum memories. There is no reason why it should not be possible to develop quantum memories. Some exist, but they are not very good nowadays. And when you have a quantum memory, you can do quantum teleportation. Okay, the point I wanted to make is that by thinking of non-locality, I know immediately that I need a quantum memory. Otherwise, you do big calculation, and at the end of the calculation, you come to the conclusion that you need a quantum memory. Okay. Okay, to finish, do we have a new quantum revolution? I told you yesterday already, so I will rush a little bit. Second quantum revolution is using entanglement and being able to manipulate single quantum objects. So single atom, single photon, single ions, single whatever you want, including circuits which behave like two-level system. And if it works, well, it works in part, or silicon dopants in silicon, okay, dopants in silicon. If this works, of course, now you have the scaling, which is easier. Anyway, for the time being, it does not work perfectly. So what do we have nowadays? Okay, let us pass the first quantum revolution. So we have quantum communication. Yesterday, you heard of quantum cryptography, today of quantum teleportation. Quantum cryptography works. If you need quantum cryptography, if you are rich enough, if you can pay, you can have a system of quantum cryptography, okay? Quantum teleportation demands quantum memories. By the way, why is quantum teleportation useful? Because if you have a quantum computer here, and the output of the quantum computer is a certain quantum state, if now you want to use that as the input for another quantum computer, you better teleport the state rather than trying to make a measurement which destroys a part of the information, etc. So quantum teleportation would be useful for using the output of a quantum computer at the input of the next quantum computer. Quantum computer, by the way, two kinds of quantum computers. The ideal quantum computer that does not work yet, but there are efforts to go towards this direction. And quantum simulators, which are kind of analogous quantum computer, and these one work and are exactly at the point where they may obtain the quantum advantage, that is to say, they may be able to make calculations that you cannot do with a classical computer. For instance, my friend and former PhD student, Antoine Roes, has a quantum simulator which allows him, condensed matter guy, allows him to solve the Ising problem with more than 200 particles. No classical computer can do that, okay? So he's at the limit where he can address a real, not a fake, but a real problem with his machine. The good thing is that the people on classical computer are smart, so they are developing, they know that they cannot do it with full calculation, with exact calculation. They develop approximate method, and up to now, with their approximate method, they find the same result, so it's cross-checking between them. They check that the approximate method is a good approximation, and they check that the machine of Antoine Roes is a good machine. And you have startups doing that. Well, by the way, I must say that I am a founder of the startup, so I have a conflict of interest. Like for the book, when you back the book of Einstein, I get $50, okay? So and then quantum metrology. I told you yesterday that quantum gravimeter works pretty well. Okay, so will the new quantum revolution change the world? We do not know. Will the quantum advantage be either on computing efficiency or on energy saving? We will see what happens. And I just want to show that there are plenty of people who put money in that. This is France and region of Paris, of Île-de-France. Each time I go to a different place, I look for a national program, and there is indeed a national program in this country as well. Companies which have big pockets also invest in quantum computing. And as I told you yesterday, many startup companies, and this is fascinating. Young people, if you are interested, don't hesitate, go. Thank you very much. If I was a piano player.
Well, thank you for yet another inspiring talk.
Thank you.
Questions?
Just wondering,
Microphone, in case there is something at the end of Zoom.
in the period between like EPR, the EPR paradox paper releasing and Bell's inequalities, did anyone ever investigate further like a underlying mechanics that would reduce to quantum mechanics that could explain like those hidden variables? Like, was there ever interest in that?
Yes, sure. The best example is hidden variable theory of David Bohm, which is a theory with a model with hidden variable, which is meant for reproducing all results of quantum mechanics. And the point is that when you apply it to a single particle, it's okay. You can reproduce interference fringes, etc., etc. And with two particles, what you have in it, you have non-locality. You discover that the theory of Bohm is non-local for two particles. So you have an example. So you are going to tell me why not use the theory of Bohm? And I am going to reply, why not use quantum mechanics? If I have to accept non-locality, quantum mechanics is, for me, quantum mechanics is non-local, so why not accept quantum mechanics? But you are right, people try to do. The best example is the theory of Bohm. Well, I must admit that it is limited. For instance, it can describe motion of particles. I'm not sure that it can, maybe you know better than me, the bomb theory. I'm not sure that it can describe a spin 1/2 or things like that.
Other questions?
Hello, thank you for your most inspiring talk. So you mentioned quantum memory. Is quantum memory, will it or can it violate the no cloning theorem? Meaning memory typically in the classical world, you have to copy it, like measure it and save it.
No. The no cloning theorem tells you that when I have a quantum system, I cannot, with a certain quantum state, I cannot have two systems with 2 times the same state. Quantum memory is not about that. Quantum memory is something arrives, a photon, let's say, I hide it in the quantum memory, and then I push on a button, and then you have a system emitted with that. But you see, it was only one. If you could clone, probably I said that yesterday, I don't know. If you could clone a system with its full quantum state, then you could use EPR to have faster than light signaling. Because you could, by making many copies, you could at once discover what is the polarization of the photon. You have a series of polarized like that, and you can find where it is. So all that is consistent. At the end of the day, the beauty of quantum mechanics is that it is fully consistent. Strange, but consistent. The fact that you cannot signal faster than light is consistent with the no cloning theorem and with the fact that the quantum randomness is fundamental. There is no way, you cannot force the quantum randomness. It's ultimate. And all that is necessary to be consistent with the impossibility to signal faster than light. I must admit that I am impressed by that.
So I wanted to ask about, so it's given that Einstein is wrong, we said that current understanding of quantum mechanics supports either quantum holism or quantum non-locality. And you mentioned that quantum holism supports quantum computing, whereas quantum non-locality supports quantum communication. But is this perspectives, how to put it, compatible? To my understanding, I thought it was either or, that quantum mechanics supports one or the other.
Okay, finish your question, but
well,
it's finished?
Yeah.
Okay, no, it's not either or. The only rational conclusion from the violation of Bell's inequality is that local realism has to be rejected. But you see that local realism is consistent, because when you say that two objects separated in space-time have their own physical reality, this is consistent with the fact that you cannot exchange faster than light. If you could exchange faster than light, what would it mean that here you have the full physical reality? So the fact to say I renounce reality or I renounce locality, in my opinion, it's more for your own image in your mind. But from a more fundamental point of view, the only logical thing that I can say is local realism has to be rejected. But personally, I accept a kind of inconsistent image, which is useful for me, which consists of saying, okay, I accept the idea of the physical reality of the system, but that physical reality can be affected instantaneously by something that I do here. From that image, I say, oh, if I would do that, it would be interesting. And then I take my pen and I do the calculation to see if my intuition is confirmed by the explanation. But if some people prefer to say, no, I keep locality and I renounce the idea of reality, that's their right. Everybody can use the image which are more comfortable for the person. That's my point of view. But don't say that we have to choose. I can choose because I like to choose, but nobody forces me to choose. Stephen wants to make a comment.
Saying that the world looks increasingly grim, rejecting realism is more important.
So this is a more strategic or pragmatic question, but is it, many people recognize that quantum memories will be very useful and important and that we should push to long coherence times. From the perspective of an experimental physicist who wants to make a measurement, should we be working on this, or should we, allow the industry to solve long coherence time quantum memories for us and focus on how they will be used once they exist for some fundamental physics measurement?
My point of view is that there is a continuum from basic research to industry, especially these days with all the possibility of startup, etc. And I think that we are still at the point where we need basic research labs to work on quantum memories, to develop. There are some ideas, some principles, okay? And the duty of industry is, once you have made the proof of principle in lab, it is to develop it in a reliable way. For instance, this machine, Pascal, that I showed you. Okay, the idea is Antoine Brouès has in his lab one of the best quantum simulator in the world. Okay, the only competition is Misha Lukin in Harvard. Okay, they are about the same level with Rydberg atoms, etc. Okay, but this machine demands 2 postdocs, 3 graduate students, and it works every other day, not every day. All the time they have to tweak everything. This is normal. Okay, in a research lab like that. The goal of Pascal, the startup, is to have a machine that you can put in the hands of computer scientists who do not know anything about atomic physics and about quantum optics, and they must be able, by pushing buttons, to implement some quantum algorithm. That's the duty of industry. The duty of industry is to provide apparatus which are reliable. And it's a very interesting thing. Personally, I love technology, and I would have been happy to help a machine which works 1 day out of 10 to transform it in a machine that you can give to people who do not even have a diploma in quantum physics.
I think we have time for one more question. I just want to say we missed people on this side. Okay, well, in the middle of the wending its way to both sides.
Hi, thank you very much again for your wonderful talk. I might be wrong, but I just wanted to ask you about this. I've seen some reports that there's a lot of research going into quantum memories, and there's a good amount of coherence time. But one of the problems is the amount of time it takes to read information from the quantum memories. You mentioned that it's very useful for quantum teleportation, which I imagine if data is being transmitted over long distances, taking some time. I have no idea kind of how long is a good time to read the information, especially if it's over long distances. I was wondering if you can share your thoughts on that.
Well, I'm not an expert and I'm not following all the details, but to my knowledge, the proof of principle of quantum memories are all based on system where the duration of the memory is maximum millisecond or something like that, okay? Because a dream would be the following. Take the Chinese satellite, okay? Pairs of entangled photon. Let's suppose that you send one photon here and you keep the other one in a quantum memory, and you let the satellite progress along the Earth. And after 10 minutes or 15 minutes, you send. And with that, you can have entangled photon between 2 opposite sides of the Earth, antipode. We are very far from that. But already, if we could, from a quantum computer here to another computer here, pass the information with quantum teleportation, it would be already useful, okay? And for that, you need some kind of quantum memory. Maybe it's a form of Nicolas Gisin, which is elementary, but better than nothing, having a coil of optical fiber, but it's good only for 1 qubit. So you need, but you can have a bunch of optical fiber, who knows? But I think it really is, I have a deep belief, based on my, unfortunately, too long experience, is that when something is not forbidden by a fundamental physics law, sooner or later, you get it. Engineers are very good at providing systems which are allowed by physics. If it is not allowed by physics, you better be cautious.
I think that's a wonderful note on which to end. So one more time, let's thank both of our speakers.
Merci.